everyone. My name is Ahmed Abdulatif. I am a PhD student at UPC, University Politecnica di Catalunya. And today I will walk you through our experience with using OpenACC on our hybrid architecture flow solver RHEA. So first of all, what's RHEA? RHEA is a hybrid architecture flow solver, which is designed for academia. It provides a solution for 3D conservation equations that govern the compressible fluid motion, and also enabling simulations of turbulent flows with complex physics. Our focus is mainly on the simulation of supercritical turbulent flow at microscale level, and this is under our ERC project named Scramble. However, RHEA algorithm can be adaptable depending on the required case through different thermodynamics model, defining if you are using ideal gas, steam gas, or Ping-Robinson, and also to choose from different transport coefficient models and Riemann solver schemes. So in order to get a glimpse about how the solver is written, RHEA is written in C++ and based on object-oriented programming. We use YAML and HDF5 files for the input and output operations. Also, the solver is a hybrid architecture based on MPI, and we lately introduced the OpenACC acceleration computational framework, which we target with the GPU. And we will speak about how this implementation done in the next slide in details. So the first thing we do before accelerating or porting anything to acceleration, we need first to identify the targeted functions that it makes most of the computations, and it's inside our solver. So in our cases, when we do like profiling for the solver, we find that around 70% of the workload is distributed among two functions, the one named inviscid flux function and viscous flux function. So this is what brings us to the idea that we need to enhance the computational performance of these two functions. But first, before thinking what's the algorithm that we want to use, a framework, we define 3 points that will make our decision. So for us, it was why OpenACC. So our decision first was because it's a straightforward, meaning it preserves the sequentiality of the code while taking into account the hardware capabilities. Second, the flexibility. Here with OpenACC, we have two options, whether we use the managed memory technique or the non-managed memory technique, where it's like the managed, where it's automatically managed the movement of the memory between the host and device, and the non-managed one where we are the one who control the movement. And lastly is the modularity, which gives us the opportunity to control the kernel execution based on the different applied directives, whether we want to, I think most of the attendees have kind of brief introduction about OpenACC and the different directives they use, whether it's kind of copying in or out, the collapsing directives, and so on. So the first approach that we used was the managed one, and it defines what I said earlier about the simplicity, because with the simple directives you apply on the top of your function. In our case here, it's the pragma-ACC parallel collapse loop, and this one will simply, with the compiler, of course, flag that we will use the managed option, it will automatically port in and out the function to from the host device and so on. So the second approach that we implement, we wanted to be based on the non-managed technique, where we control the movement of the data. At this level, it's a bit more work, and it needs more analysis and more profiling to know exactly what directives you need to use. And for example, in our case here, we use the copy-in data to move the arrays to the host, to the device, sorry. And then after we finish the computation, we copy out the arrays that we only need, And by this, we enhance the performance and we manage the memory more efficiently. This can be seen from using a profiling event movement, which in this case, we are using Insight Profiler for this technique. And it will help this into making you track, analyze, and monitor the applying of the construct over the function. Here, we can monitor in red, for example, the porting of the data from the host to device, and within the blue, it's telling you that the compute construct is running, and in yellow, it's showing the CUDA API calls at this moment. So it helps to give you an overview of what's going on and introduce the solver profiler better. So what are the findings that we got from this? So far, reaching these points can be, our finding can be summarized based on the testing, the implementation over the strong scaling test. For the case here, we're running over 200 million grid cells. Regarding the CPU versions, it scales well up to 16 nodes. I want to hint that all our tests that we conducted have been conducted on Barcelona supercomputer. So PSC here is abbreviation for this. So, and related to the part which is the CPU, GPU part where we accelerated our function, the function that we accelerated and we targeted scaled well. We reached speed up to 27x and 15x for the functions. However, the unaccelerated functions that we haven't addressed, and we didn't accelerate these functions due to that these functions contain pointers. And OpenACC directive is not handling well this kind of implementation of functions that contain pointers. So this brings down the whole total scaling of the solver. And for the other test, which was the weak scaling test that we performed, we kind of seen the similar behavior where the parallel efficiency for the targeted function performed flawlessly, but also the unaccelerated functions, the one that we haven't targeted, also affect the total performance of the parallel efficiency. However, what we take into consideration is the total speedup of the solver reached up to 6x. So even with the non-targeted functions that we didn't accelerate, and targeting only the two functions that takes most of the time, we reached up to 6x speedups for using the non-managed technique, and around 3x for using the managed one, which we haven't done much effort when using. For sure, applying the OpenACC approach all over the function will enhance the whole performance and increase the level of speedup. So this will bring us up to the next action, which is our future work. Our future work will simply, we need to focus on two things. The first one is we need to minimize the number of functions that depends on that exist, that has pointer inside it, and by this we can increase the number of directives that we can add and increase the speed up of the whole system. Beside also the second thing that we want to address is to enhance the computational efficiency of the MPI communications. Through using the new techniques for the new version for the MPI communication, MPI+, and also reconstructing a different communication between different kind of functions. In the end, I want to say that our solver is an open source solver that exists under GitLab project. It's called Project RHEA in this link. And our project Scramble also, which has all our work and all our latest achievements using the solver with different implementations, it's also exists under this link. So this was my presentation of how we applied our OpenACC in our solver and the results that we get. We wanted to transmit an idea that it was kind of not easy. It was easy to use with the managed one, And with the non-managed, it requires more work, but it's doable, and the results that you can achieve with a small introduce in the code is remarkable. Thank you, everyone, and I'm open to questions.